We go. You missed the here we. I think I said that before the recorder started. In any event, we are on section 12.6, dealing with phase changes. And in the beginning of this video, we're just going to talk about liquid to gas, which would be called boiling or evaporation. Later we will talk about liquid solid and solid gas. All right, first thing, vapor pressure. Definition. All right, vapor pressure. This is a little bit of a confusing concept, so I'm going to show you some pictures to describe it, and hopefully it'll make sense. Vapor pressure is the pressure that a liquid exerts above its liquid phase in a closed container, and it is dependent on temperature. So here's a picture. So we have a container right here. Let me switch over to the arrow so that I don't accidentally erase something. So here we have our container. We've closed the container, and there's a liquid in here, and you create a vacuum up here, and you allow this liquid to evaporate. It just evaporates until we're not at equilibrium yet. At some point there's an equilibrium between the gas and the liquid phases. And that means that the liquid molecules are leaving the liquid phase, and the gas molecules are entering the gas phase. There's arrows, are hard to see, arrows pointing up and arrows pointing down, and they're leaving the liquid and entering the liquid at exactly the same rate, which means you're at equilibrium. And when there's an equilibrium between the liquid and the gas phase, that gas pressure can be measured, and it's called the vapor pressure of the liquid. So this is just a way that you measure the vapor pressure of a liquid, and it's a physical characteristic of liquids. And the vapor pressure of liquids depend on temperature, and you can measure vapor pressure versus temperature. This is how we measure vapor pressure. So we have initial conditions. This is how this example is for water. You put some liquid water in a container, and you have a manometer or a barometer. I think this is a barometer. So right now the pressures are the same. You put that liquid water in there, and you know these pressures up here and in here are the same because the mercury liquid is equal. That's Hg for mercury. Now the water starts evaporating. It's not at equilibrium yet. So the vapor pressure is starting to show up, because right now you can't see what it actually is. We shouldn't say the vapor pressure is increasing. It's the pressure is increasing up here. And now we get to equilibrium. So the pressure of the gas up here, it's caused by liquid water molecules going to gaseous water molecules. And those gas molecules cause a pressure to be exerted in this area, and it pushes the mercury down. And the difference in height between this side and this side is the vapor pressure of the liquid water at whatever temperature that this experiment is being run at. And that is one way to measure vapor pressure. And we'll probably do a lab where we measure vapor pressure. Okay, very important. The vapor pressure depends only on temperature and whatever substance you have. But it's substance dependent and temperature dependent. It is not surface area dependent. So this liquid water, if this container here was twice as big, the vapor pressure would still be the same. So here's a pictorial on the left side showing you, here's some water with a very small surface area. Here's some water with a great big surface area. And we've closed these containers, closed the container. Same temperature, they're both at 25 degrees Celsius. And the vapor pressure is the same in both containers, whether you have a small surface area or a large surface area. Same vapor pressure. At 25 Celsius, the vapor pressure of water is always 23.8 torr, or 23.8 millimeters mercury. Okay, this graph on the right side is showing you temperature is increasing along the x-axis, and vapor pressure in, I believe that says millimeters of mercury, is increasing along the y-axis. And there are different chemicals. We have pentane. So notice as temperature goes up, vapor pressure goes up. So pentane is here, here's hexane, here's heptane, and here's octane. Now notice, pentane has a lower total number of electrons than hexane, so these are both nonpolar. They both have only London dispersion forces. These have stronger London dispersion forces because it's a larger molecule. And therefore, at the same temperature, let's go, at the same temperature, notice hexane's vapor pressure is lower because the forces, the intermolecular forces, are holding those molecules together better, so fewer molecules leave the liquid phase to go to the gas phase. Whereas for pentane, it has a higher vapor pressure at the same temperature, has a higher vapor pressure, almost 450 at 20 degrees Celsius, whereas hexane has a vapor pressure of only about 140 millimeters mercury at 20 degrees Celsius, because hexane has stronger London dispersion forces. Now, boiling points. Liquids boil when their vapor pressure is equal to the outside pressure. This is extremely important. You should write that down. I don't think it's written down anywhere here. So, a liquid boils when its vapor pressure equals the outside pressure. So let's look here. 760, 1 atmosphere. That's where we live. We call that the normal boiling point. So the normal boiling point for pentane is at the temperature where this line intersects 760 millimeters mercury. So right here, 36 degrees Celsius. Hexane boils at a much higher temperature because it has stronger dispersion forces. Heptane, even stronger dispersion forces, boils at an even higher temperature, 98-ish degrees Celsius. Okay. Oh, there we go. A liquid boils when its vapor pressure equals the outside pressure. Make sure you wrote that down in your notes. Okay, what is the vapor pressure of pure water at 100 degrees Celsius? Well, I just told you that a liquid boils when its vapor pressure equals the outside pressure. So the vapor pressure of pure water, we know that water, hopefully, I hope you know that water boils at 100 degrees Celsius normally. So 760 millimeters mercury, 1 atmosphere. Water boils at 100 degrees Celsius. That's the normal boiling point, 760 millimeters mercury, or 1 atmosphere. Okay. Next page. We're going to move on to something called phase diagrams. So now we're going to talk about solid to liquid and solids to gases, and vice versa. There is something called a phase diagram. There's a lot of information on here. So a phase diagram is a diagram that shows you where a substance would be a solid, a liquid, or a gas. And all the information is shown with the letters. So B is where you have a solid phase. So all in that range is solid. Everything in this E area is a gas. Everything in the D area is a liquid. Now I'm about to say something that really shouldn't show up on videos. However, I heard this at an AP conference. If you ever forget what goes where, just remember that gas comes out of the butt. And when you see a phase diagram, they almost always look a little bit like a butt. So we have our gas coming out of the butt. Okay, hopefully you're laughing. Aside from that, we have a lot more information on this. There is something called the triple point. A. This point right here is called the triple point because on that point you have the solid, liquid, and gas all present. So along any line you have 2 phases present. When you're not on a line you have only 1 phase. So anywhere in here you have only a liquid present. So at 50 degrees, 3 atmospheres, for whatever substance this is, it would be a liquid. 50 degrees in 1 atmosphere, the substance would be a gas. 10 degrees, 2 atmospheres, this substance would be a solid. I hope you are understanding how to read this phase diagram. Along a line, you are at equilibrium between two phases. So line F would be the liquid-gas equilibrium, line C, solid-liquid equilibrium, line G, solid-gas equilibrium. And the names for these transitions are also listed here. Freezing, melting, boiling, condensation, sublimation, deposition. These are usually new terms for students. Then there's this point H. What is that? It's called the critical point. And here you go. Critical pressure. So you go to the critical point and the pressure, it's about 4 atmospheres for the substance. The critical pressure is the pressure needed to liquefy a gas at the critical temperature. And the critical temperature is the temperature above which a gas cannot be compressed into a liquid. So if you are above 100 degrees for this particular substance, it will remain a gas. So if you're up here, you're a gas. Anywhere up here. Over here, you're not a gas. Up here, you're a gas. Anywhere up here, you are a gas. And if you're at this 100 degrees, you need to bring the pressure all the way down to 4 atmospheres to get it to be a liquid. Okay. Oh, hang on, let's bring this back. I didn't realize. There's some more information about phase diagrams. This is another picture showing you almost exactly the same information. It's just showing you which direction you're going for vaporization would be liquid to gas, condensation would be gas to liquid, sublimation, this word, solid to gas. And if you go gas over across this line to a solid, that is called deposition. And then I've just given you from B to A is the liquid-gas equilibrium, A to D is the solid-liquid equilibrium, A to C is the solid-gas equilibrium. Okay, more phase diagrams. Just a couple more to look at. We might use them in class for some questions. This is the actual phase diagram for water. The actual pressures and temperatures are not given to you. This is the phase diagram with pressures and temperatures given for carbon dioxide. Now, these are not always given to scale. The phase diagrams are kind of interesting, how they're written out typically. Okay, yeah, because if from here to here is 5, then from here to here would not be another 60. It would only be about 10 or 15. So usually phase diagrams are written kind of strangely. The more important piece here is the slope of this line tells you if the solid or liquid is more dense. If you're on the solid-liquid line, all you need to do to figure out which phase, the liquid or the gas, is more dense is you just increase pressure. So pressure goes up this way. Well, notice on this one, as you increase pressure, you go into the liquid phase, which means the liquid is more dense. As pressure goes up, the substance is getting more dense. So for this, for water, as pressure increases, you can go any point on this line. As you increase pressure, you're going into the liquid phase. So the liquid is more dense. Over here, if you increase pressure anywhere on the solid-liquid line, you increase pressure and you are more dense. So for carbon dioxide, the solid is more dense than the liquid. All right. Time for some questions. So here's a phase diagram, and you're going to answer these questions. Now, I would advise you to pause the video and look at your notes and answer these questions. I'm about to put up all the answers, so pause the video. Pause the video. Okay, here's all the answers. Let's go over this real quick. Critical, and you can just skip over if you got it. So here's our critical point, the critical temperature. Now notice it's between 100 and 1,000, and here's the 100 mark right here. I wrote 200, anything between 100 and 1,000, but you know, it's on a logarithmic scale here. It's hard to really see it, but anyway, around 200 atmospheres. Units are important. And then temperature, it's right around 650. They're showing you, notice the marks at the bottom and up at the top. So this right here would be 650. It's a little less than that. triple point, the pressure of the triple point, it's a little lower than 0.01. Anything near 0.01 is acceptable. And the temperature, you know, you got to estimate 270-ish Kelvin. Boiling point, the normal boiling point, that means at 1 atmosphere. So we go to 1 atmosphere, we come straight down. It's around 370, 380. Normal melting point, melting would be solid liquid. So you go to that line right there, come straight down. It's right around 270 Kelvin. At 10 atmospheres, it's asking for the boiling point. So you got to be careful. We're going over to here. Let's see, sorry, 1 atmosphere. The boiling point, no, 10 atmospheres, 10 atmospheres. The boiling point, it's really more like 150. I wrote, sorry, 450. I wrote 460. Let's fix that. And I also wrote liters. Okay, we fixed that there. Can this substance go from a gas to a liquid at 0.001 atmospheres? Well, no. At 0.001 atmospheres, it can only be a solid or a gas. And the last thing, describe all the changes that occur as you heat from 200 to 600 at a pressure of 0.1 atmospheres. So you're at 0.1 atmospheres, and you come over, you stay a solid till about 270, at which point you go from a solid to a liquid, called melting, and then you stay a liquid, and then you boil or evaporate at about 320-ish, and then you stay a gas. That's it. Okay, last section, colligative properties. This is in chapter 13. We just skipped a whole bunch of chapter 13 and skipped over to 13.6. These are properties that depend only on the number of solute particles in a solution and not on the properties of the solute itself. When I say solute, I'm talking about something dissolved in a solid. We've already talked about solutes and solvents. Solutes are things that are dissolved in liquids. Whatever is present in a smaller number of moles would be your solute. The solvent would be the thing that's present in more abundance. Okay, there are 3 colligative properties we're going to talk about. Vapor pressure lowering. Remember, vapor pressure is that equilibrium pressure that occurs between a liquid and its vapor above the liquid in a closed container. It turns out when you dissolve solutes, non-volatile means they don't evaporate. If you put a solute that won't evaporate into a liquid, the liquid's vapor pressure goes down. This affects the freezing and the boiling point of those liquids. Causes the freezing point to decrease. Do you know freezing and melting are the same temperature? So when you see T melt or T freeze, same exact temperature. T boil or T condense, if you condense or you evaporate, happens at the same temperature. So the boiling point elevation, boiling point goes up with when solute particles go up. And there's an equation for this. You can just read that. Just an equation. Change in boiling point is equal to the Van 't Hoff factor. It's the number of particles a substance can split into. We'll go over that a little bit. KB, you look these up in a table. M in italics is molality. It's like molarity, but it's mole solute per kilogram of solvent, not per liter of solution. A little bit different. Then we have freezing point depression. Same equation, looks exactly the same. It's just that we have a freezing point depression constant instead of a boiling point elevation constant. And I've put a little table in here. I have a whole bunch of freezing point depression, boiling point elevation constants. So if you have any problems for these particular chemicals, you can just look this up. So, oops. We're going to look at this Van 't Hoff factor, I. So if I have NaCl, it's an ionic compound. When it dissolves, it splits into 2 particles, 1, 2. I is 2. If I have something like C6H12O6, that's a molecule. Molecules don't split apart. We're going to think of molecules as not splitting apart at all. When you dissolve sugar in your coffee, those sugar particles still say sugar. They just dissolve and they don't stick together anymore. So that's I is just 1. Those do not split apart. All right. Beryllium iodide. That stuff is soluble. It's going to split out into 1, 2, 3 particles. Okay, you do the rest of them. I'll fill it in a moment. Okay, you might want to pause this. I'm about to fill it in. Here I go. Okay, so notice this was a molecule, and this was a molecule. Molecules don't split apart. Ionic compounds split apart. So it's the ionic compounds. You just add up the subscripts. Oh, careful with polyatomic ions. If I had something like, I don't have anywhere to draw this. I'm going to stick one up here on the top. Something like BE3. Oh, this is not soluble. Sorry. Na3PO4. You should recognize the phosphate would be 1 particle, and then I'd have 3 more for the sodium, so I for that would be 4. Okay, moving on, we're going to do some problems using these equations. Okay, they're not so difficult, but you have to understand how to use the equation and how to solve the problems. Number 1, what's the molar mass of a non-dissociating, means it doesn't break apart, so I equals 1, substance if 651 grams causes the freezing point of 2505 grams of water to drop to negative 7.79 degrees Celsius. Whew! Okay, we're going to have to use the equation. Delta TF is IKFM. Where students get stuck is knowing which part is the solute and which is the solvent. So the 651 grams is your solute. The water, more stuff, is the solvent. And you have to memorize the equation for molality, moles solute per kilogram solvent. Okay, so we will use this equation to solve for molality. And then we're going to use the molality equation to solve for moles. And molar mass is just the grams of the solute over the moles of the solute. And this is how many grams caused this temperature change, and this equation lets us solve how many moles caused the temperature change. Well, those moles and these grams are equivalent, so we know that that many grams is equal to however many moles we solve for. So let's plug it in. So you have to look up where water normally freezes at. So we look in this table, water, freezing point. Hopefully you know it's 0. If you don't, now you do. And here's our KF, degrees Celsius per mol. Oh, that's funny how that worked out. They'll say degrees Celsius per mol. So KF for water is 1.86. We use the KF, not the KB, because we're looking at freezing. Okay, so here's the new freezing point. I was 1, they told us that. Here's the freezing point depression constant we just looked up. And molality is what we're going to look for because we need to find the moles in order to find molar mass. Solve for molality, and now we have our equation. Molality is moles solute per kilogram of solvent. Here's our solvent right here. Kilograms, remember to convert to kilograms. And so molar mass, we solve for the moles. Solve this equation for moles. And the molar mass is just the grams that we started with divided by the moles that we calculated from this equation. Okay, there's our answer. Now you try number 2. You should pause this. I've got the solutions right below, and I'm about to show you the solutions. So go ahead and pause now. Pause. Pause. Okay, here's the solutions. And I'm moving forward. Next problem. If you needed to look at those, you can. You can pause the screen and check your solutions. I might have done something wrong. You can check my work. Okay, number 3. What is the Van 't Hoff factor for a substance if 0.5 moles causes the freezing point of 250 grams of water to drop to negative 7.44 degrees Celsius? We have water again. We'll use the KF for water. Water is our solvent, so we're going to use these kilograms. We have our moles, so we can get molality. We just plug everything into our equation. If you want to do this on your own, stop looking at this, pause, and do it on your own. But you just plug everything right into the Delta TF is IKFM equation. So molality, moles per kilogram. KF is right here. Here's your delta TF. And we're just going to solve for I, and very easy. I is 2. Could it be beryllium iodide? No, because I is 3 for beryllium iodide. And we're done.